Hi guys, I'm Nate from Good Mayhem Racing. The Forerunner that we raced the Baja 1000 in is right here, and I am working on the fourth cam tab mount down there. I'm gonna do all of this in one take because I really don't like editing and it's late tonight, so I'm gonna try to do this timely. These are my new and improved cam tab plates. You see these weird cuts? That is what's necessary to actually fit it in the truck. And the subframe that's in the area next to the rack and pinion steering is actually a different weldment profile in the back as it is in the front. So the front has a different cut path here. But these look fundamentally different from these. These are the front section of the subframe, and this weld right here and this weld right here hold these little cam holders in place. These are the rails that hold your alignment adjuster. These are octagons. The OEM ones are round, much like these. So these things slide around on the inside like this. They go around and around, and that's how you can align the truck. Well, with these octagonal plates, you can have a very consistent alignment, but because everything becomes rigid, it's going to cause something to fail on the truck. So these plates are what I want to actually fail rather than the subframe that failed previously. This material that you're going to see me fabricate this stuff out of is something called 4130. This material is in its annealed condition, which is relatively a low strength condition of this 4130. And after you weld it, you can heat treat it to improve those mechanical properties. A lot of people think that a heat treatment is necessary to boost the properties, but there are three different kinds. You have your process of bringing it up to a very high temperature, normalizing, and then quenching it like you would a sword, and then tempering it to get a less brittle condition and be very tough and very strong. Well, when you're at the annealed state of it, it is a relatively tough condition of the 4130, just not as strong as what you will get with tempering. At the same time, whenever you weld on it, you still need a preheat, a way to heat up the metal before you weld it, and you also need a stress relief, a process by which you can reduce the residual stresses from that weld that you did on these parts. These have a heat affected zone. Actually, in the grinding here, if you look really closely in the light, you're going to see a tiny, tiny line going around about 3/4 of an inch wide. That's an exaggeration, about a 1/2 inch, sorry, about a 1/2 inch wide, and that is near either the fusion line, where the weld metal touches base metal, or it's the heat affected zone, the area that's actually harder than everything else. Your stress relief will help reduce the hardness there, but really that stress relief is just trying to take off the most intense stress risers that are intrinsic to your material. For example, this little bit of cold lap right here on the edge of this weld, I'll fix that before I heat treat, but if that was underneath inside of this weldment, that could be a source for a crack. Fortunately, that's just my start and stop. I can grind it off, make it go away, and make it look nice and pretty like that side. But the stress relief stops the flaws in the weld from growing over time with fatigue, with the truck being pounded from racing use. And that actually is kind of the foundational logic of welding any type of higher strength alloy, 4130, 8630, F22, 9 chrome, 2 1/4 chrome, 1 moly, all of that stuff. You preheat it, you weld it, and you stress relieve it, but that stress relief is kind of a misnomer. The formal terminology is a post-weld heat treatment. If you see this material right here, let me make sure it's in frame. Yep. This is also 4130. But instead of being a 1/4 inch thick this time, it's 2 inches thick. And this, you see right here, this is weld. If my weld is this little tiny 1/4 inch fillet, imagine all of the residual stress that comes from welding hundreds of weld beads on something. Now you really need to get it hot and for a long time to get that heat affected zone, that area that's right outside of where the weld metal touches the base metal, to soften. That is a formal post-weld heat treat, not merely a stress relief. The stress relief just takes the high hardness, the highest brittle nature of these materials, and gets them softer. A formal post-weld heat treat actually has a real deal hardness criteria, as in this weld cannot be harder than this, the base metal can't be harder than that, and the heat affected zone cannot be harder than the other criteria that would be listed. So a stress relief, you don't have that kind of stringent criteria. With a post-weld heat treat, you do. So when you hear people talk about stress relieving, it's usually a more secretive, a shop figured it out type of criteria, where a post-weld heat treat is a formalized standard practice that people follow for welding. Back to welding my actual plates though. How are we going to do this? I'm going to back this up a little bit. Make sure we get all of this stuff in view. These little pieces have not been ground yet. They still have their mill scale. This has been ground. The mill scale has been taken off on the areas we're going to weld. We really don't care about the rest of it for now, but the cleaner your base metal is, the easier it is to weld. This is the back. This is the front. Now you know. These pieces I'm not going to weld for the very keen-eyed. These are impact Sharpies. That's from a scrapped welding procedure qualification a long time ago. Let's grind these things, get them prepped, fit them up in these parts, and we will weld them. Let's go. You need a tiger disc, a sanding wheel, a grinding wheel, something to take off this material. And I'm simply going to clamp it, grind it. This is the smooth side. These were laser cut, so I'm going to take off and grind the side that has the flashing, the slag or dross, if you will, from the laser. Okay, that's clean. Next up, I'm going to be welding on the back side of it. So this area that's notched, I'm going to grind that too. The pass-fail criteria for the grinding job on this is whether or not it fits in the hole. It fits. Fits rather nicely. If I pull up another one where I have not cut off that slag from the laser, it's a lot harder to fit. It's not very nice. Doesn't sit flat, doesn't sit square. So I have to do that prep on everything. Another one. I have 4 to do, 2 per control arm mount. Switch. Okay, this one is much cleaner. Check whether it goes or does not go. It is in, therefore it is good. Next up, this side. This is the side with the slag. Move it. So prepping like this is very repetitive. It is time well spent because welding over mill scale is very difficult when you are TIG welding. That's the process we are going to use today. Laser side, clamp it down. Oh yeah, we need to check the go, no go of our last piece. And that is good. Nice and flat. That one had an extra bit of flash on it. One more to go. Okay. Go, no go. Fits, great. The actual slop and tolerance on this thing is around 15 thousandths of an inch, as in the physical gap. You can see there that little black line. That way you have guaranteed fit up. The backside though is much deeper. This is about an 1/8 inch deep, the actual groove. And for those who are familiar with welding code, this would technically be a socket weld on this side, and this would be a fillet weld on here. We're going to weld the outside of it, not the inside, because the inside's where the work done. The outside is where the weld's done. See how this is nice and smooth? The weld is not easily visible. This is the after. That is the before. Got it? 4130, you need to have thick welds. That way you are forced to do multiple welds to have a lower stress part. Let's begin. Okay. That's in frame. That also in frame? Yeah, great. Okay. I'm going to use these as load spreaders for a clamp. I'm going to use my octagonal pieces rather than Toyota's OEM cam tab setup for this fit up. These are shallower than the plates. That way they don't accidentally cause a tolerance issue later, like bow these things out on its own. I'm going to physically clamp these things down. When it comes to fabrication, most people are obsessed with shapes and making sure that everything is fitting up correctly. In real terms though, the more you clamp something, the more hardness you're going to have to deal with. So the more you constrain something, the more intrinsic restraint it will have later. Keep that in mind. It's not really important for what we're doing here, but when you get into the hardcore side of welding where everything gets qualified, that's something to think about. The flash is off of these parts, and since I'm going to do the fillet weld on the outside, the mill scale is going to go to the inside of this tab, and the nice ground surface is going to be on the outside. Cam tab eliminator goes in, flip these things over, and let's get them lined up. For Total Chaos's version, they recommend welding the backside first. I agree. That is the more accurate way to maintain fit up in this part. And when I say fit up, that's the idea of making sure that something is dimensionally stable for welding. You put things together in a certain shape, clamp it, tack it, make sure the parts aren't moving around, and then you weld it up. That's plenty good. Excuse me. Do I got enough room? Barely. Ooh, that's close. Close enough for government work. Hooray. All right. So there are many ways to clamp something down for welding, but this little 3-bar model, post, post, and middle, is a very fast way to make sure stuff stays lined up. Clamp it down for all it's worth, and that is in place. These little pieces right here, I'm just using to diffuse the load of the clamp from this surface to this surface. And even though it's one plate, because this is a kind of a 3-dimensional bending problem, distortion this way, and that way, keep that in mind for your own use. Okay. Let's check the fit up here. Get this clamp out and up. Okay. You can fine-tune the fitment if you have the tolerance for it. Okay. I like to middle stuff as best I can. This one I have bias to one side, so I'm going to move these cam tabs physically down. Loosen it up a tiny bit. Okay, those are middled. Cool. Okay. My material is pretty flat. Let me show you what that looks like. So the actual joint prep for these socket welds, these square groove welds, is a 1/4 inch wide by an 1/8 inch deep. And now come under here and you can see the plates look pretty square, all thanks to our grinding of that laser dross, that flashing, that slag, that ugly stuff. All right. Next up, welding 4130. 2 big things to think about. 1, you need to have a preheat, and then 2, you need to do multiple weld beads. Granted, pro shops like Hamburg Engineering or Total Chaos and stuff, they would manufacture something with 1 bead everywhere they can, and they probably have a very good process control for that. For what we are doing here, this joint is so big, you're probably not going to be able to do this in a single pass. These physical beads are a 1/4 inch in size, and then this groove is a 1/4 inch wide by a 1/8 inch deep. If you are doing reasonably controlled TIG welding, this will take 3, if not 4 passes for every single one of these holes to fill. Make sure you got a good ground. And let's begin. Turning on my argon, I'm using a TIG welder. This is an Everlast 255 EXT. It is a fine welding machine. I like welding it with it a lot. I recommend it. No, this is not sponsored. Hopefully you can still hear me okay. Still recording? Good. All right. I am using a number 8 gas cup. I'm welding with ER70S2. Nothing crazy. I do not need a high strength wire for this because I'm going to be doing so many passes on this weldment, and because of the joint type, there's going to be a lot of dilution or base metal stirring and pickup that I can rely on for strength inside the weld. To prevent these tabs from bending outwards too far, you can actually choose your bead sequence on where your weld beads go first with respect to distortion. And the second thing I forgot to mention earlier is preheating. Preheating is the idea of heating up the metal to stop it from cooling too fast. The actual metal quenches the weld and the surrounding material, and that surrounding material is the heat affected zone, what we were talking about earlier. So I'm going to preheat this up to at least 200 degrees Fahrenheit. In a shop, you would have stuff like thermocouples, temperature probes, or special wax crayons that melt at certain temperatures. We call them temple sticks. Whenever you're welding alone in a shop like this, if you can preheat the part and then zap it with water, if the water flash evaporates, you know it's over 200 degrees Fahrenheit, which is good in our case. Just make that water disappear, make it evaporate away. We're going to focus on this area here first before we weld something else. Ooh, that's fun. All right. We're still in frame? Good. All right, so my first weld bead is going to be inside to the control arm, or to the cam tab, so then it pulls it inwards. I am using a Speed Glass GS05 or whatever it's called, welding hood. It's amazing. All right, fill and chill. Start moving. And your goal is to get fusion. You want as much base metal pickup as you can in the shortest amount of time, reducing the amount of heat that you're inputting to the part. We physically call it heat input. I have my purge going on for about 6 or 10 seconds, and that's more to protect the TIG, the tungsten electrode, rather than the weldment underneath. The weld looks relatively clean, and now I'm going to weld this part right here. And because this is a sharp ledge falling into a hole, I'm going to travel slower here than I did here. A good fabricator would set this up to where, like if they could, to have all of their starts and stops in different areas, but since we're only over this 1 to 2 inch long area, you can only do so much with that. I'm going to start from one side and end on the other. Here we go. Now, before I dip my wire in, I'm going to wait an extra long time, so then this flat 90-degree wall melts into the floor of my weldment. Safety glasses are fogging up. All right, here we go. Wait, start, fill it up, go. And make sure to get to the very bottom of the joint. If that means filling in less wire, that's fine. You want good penetration out of this, and keep the tungsten as deep down as you can. If you have a way to measure voltage, it'll be around 10 to 12 volts. Now add wire. Okay, slowly taper off. The slower you stop your arc, the less you will need to grind your starts and stops. You can see how that start and stop has no solidification crack at all. If you are in a regular manufacturing shop where you're worried about pass-fail criteria, you'll probably be grinding those starts and stops. Okay, need a wire brush. Let's check to make sure that we don't have any silica beads or silicon islands that are up there. Okay, it's looking very pretty, very nice. And you can see that the heat is more focused on where I'm stopping up here, but this blue hue is going to keep growing that way as time goes on. In the world of knife making, you can actually use this color to determine the actual temperature of the part. Like this is room temp, this is 400. and then this is up to 500, 600, and 700 plus. But when it comes to materials that are 1/4 inch thick and thicker, you really need a temp stick to get accurate readings or a temperature probe like a thermocouple. This is merely a surface condition, not through the thickness of your material. And that's actually the reason why other manufacturing or other industries stopped using materials like 4130, because their through hardenability wasn't as consistent as some of the more modern alloys. Because the area outside would be at a certain temp and the stuff inside would not. After a while, the very tip of your TIG filler is going to be oxidized. Clean it off, cut it off if it's really bad. And while you're still hot, weld again. This is my third weld bead. It's going to be something called a cap pass, the last bit. And because of the heat that I'm going to be exposed to, I'm going to add a little bit of protection for my fingers. This here is just kind of like a silica blanket that's made for your fingers. And I'm just going to hide everything behind there while I weld. So in industry, when we wonder about the temperature or the how hot the part is during our welding, we call that interpass temperature. Preheat is the heat before you weld. Interpass is the temperature while you are welding. Fill and chill, make sure you get that puddle started. And now we're going to weave back and forth, making sure we cover all of our previous weld beads. Making sure we don't leave any grooves or valleys, stuff that we don't have to fill up later. Make sure you don't burn your fingers. You could really do that here. As soon as I've filled it up, let's taper it off. Slowly turn off that arc. While it's glowing red hot, you can use the argon to help prevent that oxidation from getting too thick. You can see these little tiny black dots on the surface here. Those are silica beads from the welding rod. There's a lot of silicon in 70S2, and it helps with wettability, the material getting wet. All right, we finished welding this one, and it has been welded with a good preheat and a high interpass temperature. Now let's make sure the other side of this is okay. Good, it is evaporating water, kind of. The material at the very bottom of it actually still has water, which means it's below 200 degrees, or the boiling point of water. So let's heat it up so we can get that to evaporate. Again, a temperature probe or a temp stick is a much better way to control this process. And in manufacturing, it's required most of the time. At least in the world that actually requires qualified welding, like oil and gas, or shipbuilding, building aircraft carriers, nuclear submarines, oil refineries, all that jazz. Okay, I'm going to switch to my left hand so then I can weld into that hole. Remember, I want to weld the inside bead first, so then I pull that material towards the center. And I'm going to clean off that filler of the oxidized end. Oh yeah, these Knipex cutters are amazing. Okay. Oh, if you're wondering what amperage I'm at right now, it's at a humble 175 amps. Not a lot, but it's plenty for filling this thing up. Okay, weld on. Make sure I get to the very bottom of the bevel, to the square groove. Okay. All right, I got a really nice weld puddle. Getting my wire in. And I'm not doing a lay wire technique, but I'm not dabbing the filler metal into it either, because that would be much easier to do with 1/8 TIG rod rather than 332. I am using 332 here. I am pushing it in, physically ramming it into the weld puddle where it's going to melt. Start, make sure the cave starts, that the weld digs deep into that parent material, and now I can dab it. You can hear that little click. That's the filler metal melting into the puddle right next to the arc. Okay, fill up that start and stop. Give it a little whirl and a slow stop. Again, the slower your arcs stop, the less solidification cracks you're going to have, and the less grinding of your starts and stops you will need. Now, if you're doing like phase array criteria or a liquid penetrant criteria, that'll be the most likely place to fail. So keep that in mind if you're doing this in an industrial setting. Ooh, that epitaxial grain growth is really pretty. Let me show you what that looks like. Welds solidify and they have grains. So if you're lucky and you've welded well, you can actually see a reverse chevron-like shape here. You see how it's going that way versus the weld puddle? That is the material solidifying and showing off its grain structure. That is beautiful. Gosh, that's gorgeous. So the faster you weld, the more aggressive that chevron profile is going to look, and the slower you go, the more 90 degrees it's going to be. But yeah, if you want to Google that, epitaxial grain growth. Man, that's cool. If you weld with a heat input that's too high, that's very hard to see. Cut off that oxidized end. Get our TIG fingers to protect us. All right, this is going to be our cap pass. The final weld bead of this side. I'm going to start the weave, or oscillation if this was mechanized. Weaving the torch back and forth. Some guys walk the cup. I actually suck at that. I'm way better at weaving it back and forth. And I'm just dabbing the wire as stably as I can to fill up the remaining material. I'm not trying to make it super tall. I like to have a really tall cap pass. I'm just trying to fill it up so I can grind it flush later. Remember how this is shaped? You don't even see it anymore on this plate because it's been ground flush. All right, this plate has been welded. We will do the fillet welds on the other side later. Now it is time to work on this plate here. I would usually have these things spaced out and have more room, but since we're doing this in a video, I wanted to make sure you guys could see everything in frame. All right, this material looks nice and clean. Actually, hold up, there's a little bit of dust on it. Dust is bad for welding, so is paint. However, you can weld through paint if you have a high enough heat. It just really stinks and becomes a health hazard. So now I'm preheating this weld. Again, I want it to be around 200 degrees. And while heat transfers from one side of a part to another, it very rarely transfers from two separate parts. So even though this thing got really nice and hot, This had nothing. I said it before, and I'm going to say it again, temperature probes and thermocouples and temple sticks are the way to go for checking your preheats. This is the quickest and dirtiest way you can do it for free in a shop. And the higher you preheat, the softer the 4130 will be. And that, by all counts, is not a bad thing. Cut the oxidized tip off of the TIG rod. Check the tungsten, make sure it's still nice and clean. All right, let's get to welding. Ooh, that one was very nice. I preheated this one a little hotter than the last one. Okay, I'm doing a stringer bead here, a straight line, dabbing in the filler rod, twisting it around the corner, and turning it off. Okay, I'm probably going to run out of TIG rod on this next pass. Okay, let that puddle start, add some wire, make sure it falls in the hole so we can fill up this square bevel. And now we're getting good dabs. You can hear the little tick, tick, tick of the filler rod melting right next to the arc. Slow arc off. My fingers are burning really bad. All of my hands are toasty because I'm putting my hand on a hot plate, and of course that. I don't know, can you still see anything from there? Here, let's give you a better view. All right. Okay, new TIG rod. By the way, the TIG rod is provided by Midalloy. Thank you so much, Midalloy, for the help. Check them out if you need low alloy, stainless, and other types of filler for your industry. All right, this is the cap pass. So this one's, I'm going to be weaving back and forth. Get a good weld puddle. All right, now we're going. You can hear that little tick, tick, tick of the wire tapping in. That's lovely. Oh, my hand burns, my hand burns. Ow, 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 ow. Ow! Ow, 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 ow. Ow! Okay. This thing is really hot. And that part is really done. Okay. I'm going to get this out of here for safety's sake because that's hurting. You can also check the inner pass temperature of your weldment with a receipt. These things are usually heat sensitive. You can physically touch it and it turns black. You know it's over 400 degrees Fahrenheit. 400 and what's that? Fahrenheit 451, 481, whatever that book is. That's the burning temperature of paper. Yeah, you can use that as a standard too. Not just water vapor. Quick check the water. The bottom is barely collecting any material, so we're going to heat that up again. Get all this stuff out of the way. The higher you preheat, the less moisture you have to deal with. but there isn't really moisture inside the steel. A gentleman by the name of Mark Merzek actually did a material study way back when, because a lot of people thought there was actually like water or fluid inside the steel that when you preheated it, it came out. It's not. That's kind of old wives' tale. At the same time, you can improve your weld quality a lot just by preheating it to the point where moisture is not surrounding the part. Yes, that is a good thing. Sorry I'm not doing a fancy weld video for you. That's other people's jobs on YouTube. Alright, nice and deep weld puddle. Alright, I'm feeding the wire in faster than a dip. And as I get closer to the end, I'm having to move the TIG rod more aggressively into the hole, pointing it down more, where ideally you keep it almost like a 90-degree compared to where your TIG torch is. Alright, let's, woo, did you hear that? That means that my tungsten was just a little high off of the base metal. My voltage was practically a little high at that point. Okay. Alright, a slow arc stop. Great. Alright. Cap pass. Start a little bit outside the groove. A really good welder could just focus on filling up the groove, like perfect. The sucky part is, most of the pro welders I know can't even do that. So just focus on filling it up and going a little bit past, because that's what your stress relief is supposed to do. It's supposed to help you out there and normalize those stresses rather than filling it up the square just perfect. Alright, I'm glowing red. I'm not going to move the TIG torch. And the oxides have now covered the surface. Great. Alright. So, 3 weld beads, 3 weld beads. That's terrible. 3 weld beads over here. I'm an invalid. Okay. Great. So, welded, 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 welded. You can see those little tiny silicone islands. Those are just fine. Don't worry about them. You can see a couple of them over here as well. If you have a carbon steel wire wheel or wire brush, you can bust them off. But the faster the bristles go, the easier it gets. So by doing it manually, you can only get so far. Okay. We're going to leave this one clamped in. We're going to fold this guy over. And we are going to get ready to fillet weld these outside edges. A clamp is your friend. Not necessarily because you need it for the welding, it's just stops it from moving around. I don't need that load spreader anymore. Wasn't trying to clamp it down as a solid piece then. I'm now there. This is now solid, even though these 2 outside fillet welds have not been made yet. So, if you welded hot enough to where you formed new mill scale on the surface, you will have to grind it. But in this case, I got a wire brush. Carbon steel wire brush, not a stainless. Don't use a stainless for this. Use stainless for other things. Like aluminum, stainless steel, Inconel, Hastelloy, Monel, all that jazz. Yeah, use stainless for that. But here, carbon steel is your friend. Get it nice and clean. Again, you can check it with the Home Depot and see if it's okay. A lot of heat-sensitive ink is over 200 degrees. So we will rely on that as 200. Let's keep welding. We have our ground. We are clamped down. Great. Clip off the end of your TIG rod. You still recording? Yes, good. All right. Okay, this one you want to get the weld puddle started earlier rather than later, but you don't need a big weld bead. You just need a little one. And you're just trying to get that root filled up as fast as you can, minimizing the amount of heat you're putting into the part. You can actually calculate what that heat input is. It's the amount of energy per unit length, like kilojoules per inch or kilojoules per millimeter if you're wrong. Again, check your inner pass. Reacting yet? Yeah, good, okay. Let's keep going. Again, this is the single weld bead. This is the root of this fillet weld. This is going to require 2 beads to get it upwards of 1/4 inch thick. Cut the oxide off the filler rod. Okay, and let's start. Fill and chill. Nice. Let's go. Keep the tungsten really close in. Force that weld to wet the very bottom of this fillet weld. Okay, I'm going to add more filler now that I'm getting to the end. I got a little bit of undercut there because I missed it. And I got a glowing red heart. Glowing red part, sorry. It's fine. Don't worry about that. Okay. Wire brush. If you were in an industry that requires stuff to get ultrasonically inspected, they probably would not inspect a fillet weld like this, but this would be a great time to grind this weld and make it as smooth as possible before you do the next one. Now, there are some standards that really frown upon welding and grinding between each pass, but in general, it is a great practice to maintain if you are having to do multi-pass welding. All right, we got a wire wheel. That's done. Make sure our tungsten's okay. And cut this. Again, this is 70S2 wire made by Midalloy. All right, a nice big start and a little bit of weave. I'm actually putting the TIG rod on the top side of this weldment because that, woo, slapped my tungsten there. Ow! Hot fingers, hot fingers. Okay. I was welding great until I wasn't. I slapped the tungsten with the filler metal here. Sorry. So it's made it nice and shiny. Woo! Don't need that happening right here. So now we need to switch out the tungsten and make it clean. Pro tip. If you want to speed up your production time with your TIG welding, sharpen both sides. That way, if you mess up one, you can flip it around and work with the other. I've already used this one on both ends, so I'm just going to swap it with a new piece, a new tungsten. Today I'm using lanthanated tungsten. I prefer WS2 tungsten instead, but this is what I had readily laying around, And they weld pretty much the same, just one of them might be radioactive where the other one is not. Then again, the one that's not is way more expensive, so take it for what it's worth. Okay. My tungsten is now clean. Oxidized bit is off. My tungsten's a little far out. I'm going to push it in a little bit. The more stick out you have, the less gas coverage you have, which means the more problems with welding you get, especially with porosity and lack of fusion. Okay, let's finish this up. Start on the back third of the weld bead. Make sure it's nice. Carry along. Now I'm going to fill it up extra because I'm right at the end. Make sure I get good fusion. Slow arc off. Good. No cold lap at the end of that start stop. That weld bead could have been prettier. If I had started that a little bit further back, I could have gotten it more consistent. Okay, this side, I'm pretty certain I'm going to run out of TIG rod mid-run, but that's no excuse to just lose a TIG rod. If you're paying for this yourself, stuff's a pretty penny. A nice good stop. Feed the wire on the top side. Start this weave back and forth. And I'm just taking my time to do this cap pass. I'm pretty certain I'm going to run out of wire. That's okay. Yep, I'm out. If I can finish it with another little piece, I will. That thing is getting pretty toasty, so I'm going to give it a second and let it cool down. So whenever you want to measure inner pass temperature or the temperature between weld beads, it's always measured at the area closest to your start, not your stop, because as soon as you stop, it's going to be the highest temperature at any given point versus where you start at. So if you were to do this cylindrically, as in you weld around and around and around, wherever you start, you check your inner pass right before that. All right, let's fix this up. Now I'm going to put some extra filler rod at the very tip of this so then I can fill up my undercut from earlier. Okay, I'm just going to push it in extra fast here. Wait. Okay. That was good enough for government work. Next part. This one's had a remarkable amount of time to cool. I expect this one will be way colder than the last one. But my hand is still getting pretty burned by it, so that's cool. And the clamp, yeah, the clamp is still hot too. That's great news. What is up with my clamp? Oh. Okay. Clamp this down. Wire brush, wire brush. Again, a carbon steel wire brush. Make it bright, clean metal. And if you're manufacturing to something like NASEMRO 175 or NASEMRO 103, the sour service specifications for oil and gas and refineries, it would require to be an SP5 finish, bright white finish, but that's okay. We are here welding in a garage. So long as you're welding well, who cares? Let's check the temperature with the receipt. We are not changing the temperature and color of the receipt. Water is still good. Let's evaporate that water and get to welding. All right, here we go. A new 70S2 rod. Again, this is root. Faster you fill it up, the happier you're gonna be. Lovely. Okay, I already wire wheeled this side. Top off its preheat. In industry, whenever you preheat, usually that's going to be inspected like 3 inches away from your weld before you start. It's a really good, reliable way to make sure you don't shortcut a heat treat or shortcut a preheat. But again, garage welding, we're having fun. Ooh, that was a great start. Let's go. All right, I am just dabbing the wire barely in. I'm actually like letting it flow in around the edges of the fillet. Okay, I'm increasing that now, backing it off. Arc off, great. Lovely. That's a beautiful weld. Here, let me show you. Gorgeous. You can see all those little tiny black dots are silicon islands, silicon beads. We're gonna wire wheel that stuff off. Wire brush, sorry. And we're gonna do this one more time. Okay, check your inner pass. Great. Again, if your paper catches fire, it's over 500 degrees. Oh, cut this off. Okay. Still recording? Cool. All right. All right. Okay, so if you notice, I'm traveling way slower than I did before because I'm making a physically bigger weld bead. In general, a bigger weld bead means slower travel speeds. Unless you get into automated welding with the high deposition stuff and you get to do the really cool science projects and stuff. But that's definitely outside the scope of this video. Budamas. We're still seeing some epitaxial grain growth in this weldment. I am a fan. You might notice sparks coming off of the wire wheel or the wire brush. It's because it's still so hot that's igniting the material around it. Okay, not my best weld, but it'll be good enough. Apparently I'm left-handed today because my left-handed sides are looking better than my right. Off with the oxidation. Okay. 1, 2, dabba dabba do. Yeah, this left side's gonna look amazing. Okay, increasing my feed. Pulling it out, letting it stop. Okay. Here you can see that weld. That very pretty left-handed weld in comparison to the right. Just not as steady tonight. Left hand, right hand. It's been a long day. All right, so once we get up to room temperature, or down to room temperature, I should say, I will take these plates and I'll take these caps and grind them flat on the backside. Ooh, that's still hot. And after I'm done grinding them, off to the stress reliever post-weld heat treat. So thank you guys so much for watching. I will see you out in the desert, if not my garage. Like and subscribe for more if you like watching chromoly getting welded.